This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Hello everyone joining us around the world, and welcome to our Distinguished Lecturer Webinar Series. Before we go any further, my name is Carrie Cosby and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our more than 500 professional and student chapters around the world and manage our Distinguished Visitors Program. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. You can ask your questions in the Q&A panel. Dr. Sosa will answer as many questions as he can following the presentation. The webinar is being recorded and the slides and recording will be made available after the webinar. Today's lecture is Unconventional Computer Arithmetic for Emerging Applications and Technologies. I'd like to introduce our speaker. Leonel Sosa received a PhD in Electrical and Computer Engineering from the Instituto Superior Técnico Universidade de Lisboa in 1996. Where he is currently full professor. He is also senior researcher with the R&D Instituto de Engenharia de Sistemas e Computadores. His research interests include VLSI architectures, computer architectures, parallel computing, computer arithmetic, and signal processing systems. Dr. Sosa, I'd like to pass the floor to you.
Okay, so thank you very much, Carrie, for the nice introduction, and also I'm quite happy to be here for this presentation in the scope of the Distinguished Visitor Programs of IEEE Computer. So let's start my presentation. I will briefly just introduce where I came from. So I'm currently the head of the Electrical and Computer Engineering Department at IST. IST is the Faculty of Engineering of the University of Lisbon. So we have around less than 10,000 students in the faculty, and the whole university, we have around 55,000 students. So I'm also affiliated with the Research Institute, which is in SKD. And as Carrie said, my main interests or research topics are in the area of computer architecture, computer arithmetic, and parallel processing. So let's start the presentation by the motivation. So looking to this slide that we have here, so we just analyze or highlight the main characteristics of emerging technologies along three different axes. So the cost, the speed, the size, and also a fourth X, which is the energy per operation, which just by a matter of simplicity is represented by color. So this is a graphic or a figure that I just took off from the report of the International Technology Roadmap for Semiconductors. So this version is 2003. And it's interesting because you can see in these emerging technologies, so technologies like spin transistors, superconducting electronics, and also molecular electronics, so PCA, and optical devices. But no one of these solutions has fewer major drawback as CMOS, as you see, as you have a perspective along all the axes. So this green area in the center represents exactly what CMOS has done in the scaled way along the time till nowadays with that we have a technology with 7 nanometers. So, and then we have all of the others as good characteristics along one of the axes, but have significant drawbacks along one or several of the others. So the motivation is that if you look to this figure, which is exactly the same kind of report, but for the report from 2015, from the International Technology Roadmap for Semiconductors, you see that in these different levels, you have the material, you have the device, you have the data representation, and you have the architecture. So it's some kind of simplified scheme, but give an overview of the whole picture to design a system. And on the left side of this figure, you have the silicon path that vertically go to scaled CMOS, and then binary data representation and von Neumann architectures, as well as multi-core architectures. On the right side, you can see different material, and then devices like spintronics, quantum, molecular devices. And then at the representation level, we can see what we call non-conventional number systems or number representation and computer arithmetic. Then give, that lead to, on the top, to quantum morphic architectures. So things like PIM, so processor in memory, all the kind of architectures that we are exploring nowadays. So we are, my presentation or this talk will be focused on data representation and exactly what we call unconventional number systems and computer arithmetic. So I'm preparing a survey for the IEEE journal. So, and the organization of the paper or the survey is exactly this one that I have here. But we can see on the vertical lines in the column, on the columns, we can see the different type of arithmetics that I will present today. And then on the horizontal lines, we can see architecture or processors, and we have different ones, like for instance, nanophotonic computers, so PIM architectures, so HDC processors that we will see what does it mean. And then we have different technologies, like for instance, DNA and molecular architectures, so integrated photonics technologies, and also superconductors, and special types of CMOS devices. And on the bottom of this picture, you can see the applications. So my presentation today is a bit of the confluence of this unconventional or non-conventional computer arithmetic with new computing paradigms and emerging technologies and applications. So this is some kind of puzzle that we have to connect the pieces in the right way to get the whole pictures and be able to design real systems with new technologies, new emerging technologies, and considering the emerging, also the emerging applications. So the outline of my presentation will be, so the first 4 sections or topics or chapters will be basically on this vertical line. So I start presenting briefly the logarithmic number system. So the residue is a typo, so it should not be there. So then residue number system, stochastic computing, hyperdimensional computing, and then two different types of new computing paradigms, so linear computing and quantum computing. And then we look to real applications and see, I will give you some experimental results for lattice-based post-quantum cryptography and also machine learning. So I will talk a bit about convolutional neural networks, so implementation of this on this type of technologies or more traditional ones. And then I will finish drawing some, I will draw some conclusions from my presentation. So looking to the logarithmic number systems, so you have this table. When we consider 32 bits for the representation, so you have the traditional floating point numbers, and then you have the logarithmic number systems that in this case, we consider also 8 bits, but for the integer part, not for the exponent like in the floating point, and 32 bits for the fractional part, and we have an additional sign bit. So if you look to the fourth row, you will have exactly that the value of this number represented in logarithmic number systems is typically a power of 2 that you have the integer dot, the fractional part. If you look the minimum and the maximum values are roughly the same that you have in the floating point representation with some number of bits, which means single precision floating point representations. But the way you distribute along this range, the numbers that you are representing is different in logarithmic number systems. So what are the main advantages of this type of representation in terms of arithmetic? Is that you go to the more complex arithmetic operations, like, for instance, division, square root, the power, even multiplication, and you can do it very easily with shift and subtract operations. But you do that at the cost of more complex units for doing addition and subtraction. So typically, if you look to addition and subtraction, what you have is that you have to apply the Gaussian logarithms, which is in this expression on the left side of the slide. So you have to complete, if the basis for the logarithmic number representation is 2, so you have log 2 of 1 minus or plus 2 powers of lambda, which is lambda is the absolute value of the logarithmic representation Q and P. So what you have is that for a high number of bits, so like 32 or 64, you cannot fully represent this type of logarithms numbers in LNS by filling the lookup tables, because you have a huge amount of memory that you need. So what we did is that we just pick up and store some points, and then we apply piecewise polynomial approximation or digit serial iterative methods just to get the other values in between these stored fixed values that we have in the lookup tables. On the other hand, the other problem is that for subtracting in the logarithm number system, as you see, when we just are in the region between -1 and 0 for this lambda, as we see in the graph, we'll go to minus infinite. So you need to apply a co-transformation, or you need to apply co-transformation just to get the value in this range, or in this interval between -1 and 0. So this is good for signal processing, because when you look to signal processing, and mainly to linear processing, so you have convolution, you have addition, and you have multiplication. So the addition are not easy, as we have seen, to perform in the logarithmic domain, but the multiplication is quite easy. And you can do normalizing, because you can divide by some number very easily by doing subtraction in this domain. So what people have done is that even in the current technology, so CMOS technology, they have developed real microprocessors. And this one is so it's a typical example, a very representative example is the ELM, which means European Logarithmic Microprocessor. So it's a 32-bit scalar multiprocessor that is not register-register instruction set architecture that we have in this RISC nowadays architecture is a register memory. So we have just, to give you an idea, you have 16 general purpose registers, you have L1 data cache, and you have 2 real headers and subtractors operating in 3 clock cycles, because it's a difficult kind of operation. And then we have 4 combined multiplier, divider, square root, integer that perform this type of operation units, but just operate in 1 clock cycle. And you have vector operations, so that can use in parallel 4 of these functional units. So the fixed point LNES-based arithmetic unit is assigned bit 1 with 32 bits of fractional components and an integer part with the remaining for the 32. They just apply Taylor interpolation for addition and subtraction and have particular type of co-transformation. So I'm not going too much in detail. I will give you the general picture. And it was fabricated in 180 nanometers CMOS technology, running at 125 megahertz. and is evaluating against the DSP from Texas Instrument, which is a 320C 7700, which is also a contemporary DSP. And we see that for addition, it is only marginal better, because we use lookup tables and some kind of interpolation. For multiplication is significantly faster, so 3.4 times faster, which is using exactly the same type of technology, and division square root is several times faster than the Texas processor. So look to a real application, which is a convolutional neural networks. What we can see is that we can apply LNS just to perform to compute the convolutional neural networks, and also with activation and weights with a very small width, with only 3 bits. And it was shown that we have almost no loss in terms of classification performance, which typically we consider the mean average prediction that we have in terms of errors. So we have in the picture here, you have the scheme. So we have 3 bits. You calculate the log. We start the log of the samples. Then you have the weights in the top that you store in 4 bits, but the small amount of memory. Then you do the convolution. And to do the convolution, you have the equation just right below the picture. And what you have is that you only do bit shift and you do addition. You do addition, but it's very easy to do addition because it's the power of 2, so you can do it in logarithmic domain. The only part, so it is the addition in the logarithm domain. The only part that you don't do in the logarithm domain is the accumulation, but you can also do some approximation that the log 2 of 1 plus x is approximately x. And if you do that, you can do everything in the logarithmic domain. So let's just go forward to another type of unconventional arithmetic and representation, which is the residue number systems. And in this case, so most of you know this type of representation. So I go briefly and say you have to define what we call a moduli set, which is a set of integer numbers that are co-prime among them. So they are not prime, but they are relatively prime. So like this, you define a dynamic range, which is the product of the moduli, and you represent an integer by the residues by dividing the integer division of the number that you want to represent by each one of the moduli, and you just pick up the remainder of the integer division. So what is the main advantage? So you just pick up small integers, a set of small integers that represent the large integers. So the carry chain is splitted. You can do the computation in parallel. So if you do addition, subtraction, multiplication, you can do it in each one of the channels, and you do it in parallel, so it's much faster. If you do the division and also non-linear operations like comparison, other type of operations, not only comparison, but also sign detection and overflow, it's difficult to do because you have inter-module operation, and you don't have this type of benefits that you have for the basic multiply, addition, and subtraction operation. So this is just an example that you see in a picture. So I have a cube. I want to do some edge detection or I want to perform some operation, image processing. So I have to perform the convolution that you have on the top with this matrix or with this kernel. So we can decompose the cube in the moduli set, which is in this case 5, 6, and 7, which product is 210. And then you can perform the operation in each operation, or the operation in each one of the channels, and then you recompose again by doing reverse conversion to the original domain. So let me just go one step back and say that since you have all the rest of the world continue to be binary, you have to do binary to residual number system conversion, and residual number system conversion to binary, which is reverse conversion. And this is an overhead. So if you just perform a couple of these basic arithmetic operations in the residual number systems domain, So you don't get too much benefit because you have to perform binary and or forward and reverse conversion. So it's just worth to do it when you do several operations. So let me just start to correlate this type of arithmetic with the new or emerging technology that you have. So if you look to integrated photonics, one of the problems when you perform arithmetic is that the number of switches grow with the square of the number of bits that you have in the representation. So for instance, in this case, that is quite well known, and you have a lot of research on that, they are using 2x2 hybrid photonic plasmonic integrated switches that are fabricated using indium tin oxide as the index modulation material. So the voltage controls the guidance of the light and may operate till 400 gigahertz at the moment. But the speed is defined by the modulators, photodetectors, and also the associated electronics. So why do we apply residue number system? Because like this, we can just split the large number that is represented by hand. You can split this number in small integers. And with these small integers, you can afford it with this technology with an implementable number of switches. So in this case, in this figure, what we can see is that we have the optical path on the horizontal line. We are performing the operation model 5. So you are adding 4 plus 3, which model 5 is 2. So we go up in the level 1. Then we go down in the level 2, down again in the switch of level 3, and then it's straightforward. And this is represented by the number 3 that as a representation that go and just control the behavior of the switch in each one of the levels. And we apply it for integrated photonics, and residue number systems are quite important because otherwise it's difficult just to implement in practice the arithmetic units in this type of technology. So the other types of residue number systems that we have is redundant number systems. And so it's an extension of the traditional residue number systems that I referred before, and is used mainly for error detection and correction. So what we just take advantage is the fact that the residues are independent. So if I introduce some redundant model in my set, so the range of the legitimate model is extended to the illegitimate one, which means that I can detect errors, and in certain circumstances, I can even correct those errors. And this is quite important in emergent technologies because you have several errors and you have defects in the technology that should be detected at a higher level. And in this case, we detect them at the level of data representation. So we have, very recently, we have a core that was proposed and designed, which is the processing for YOL, creepy. So with which microarchitecture and instruction set architecture integrate this type of redundant residue number system, centered algorithms and techniques to efficiently assure that we provide mechanisms for error correction. In this work is very interesting because novel schemes are proposed also for addressing memory by using also numbers that are coded or represented in the residue number system domain. And this is quite interesting because you just close the loop and have everything inside your microprocessor using residue number system. So let's touch the third type of unconventional arithmetic that I would like to talk a bit today. And this type of representation is stochastic representation that is usually called stochastic computing. So if you consider a continuous time stochastic process, so very briefly, the value of a bit stream, which is the number of bits with the value 1 that you have over the total number of bits. So in this first figure that we have in this slide, we have 9 1 bits over the total of 15, which means that I'm representing the number 0.6. Okay, I'm simplifying a bit, so I'm using what we call in stochastic computing unipolar representation, because you have also bipolar representation, and with bipolar representation, the number that is represented with this stream of bits is a bit different. But okay, just consider that you have a unipolar representation. I'm representing numbers that are between 0 and 1, real numbers, that you can scale also for integer, but are real numbers. And you can do it with stream of bits. And this stream of bits are just generating, and this is very important, by a continuous time stochastic process. So like this is like so the position of the bits in this stream does not have any meaning. And you have several bit streams that represent exactly the same number, the same real number. And this is very important because you are introducing randomness, and also you are also introducing redundancy in the sense that you have several streams that are representing exactly the same number. And this is also important because it simplifies the arithmetic. So if you look to the figures down, multiplication is just an AND gate because you have a stream of bits. So you are doing multiplication. In this example, you have 4 over 8 multiplied by 6 over 8, and in total, so if you do it, you have 24 over 64, which means 3 over 8, and you have exactly the exact results if the stream is stochastic, real stochastic, and you have a number of bits that allow you to do exact computation. And on the right side, you have a multiplexer that if the control bit has a value of 0.5, so you are adding the 2 inputs that you have in the number that you have at the 2 inputs of the multiplexer, and you get at the output exactly the average of the sum of these 2 numbers. So it's important because the correctness is impacted by the correlation that you have between bit streams. So they cannot be at all correlated to have the exact values, and the streams has to have an enough number of bits just to assure that you have at the end the final and the exact result. So one example that I can give you is if you put the same stream at the 2 inputs of the AND gate that I gave an example of a multiplier, you should get at the output the square of the number. But since it is an AND gate, you just get exactly the same stream that you have in the 2 inputs. And why? Because they are correlated. So they have to be assured. We have to be assured that the streams are uncorrelated. And we have techniques to do that, but I'm not going to much in detail. So since you have to interface with binary representation like you have in residual number systems, you have to have converters like in residual number systems that convert from stochastic computing to binary. And we have here a very simple converter, which is you have a random number generator, then you have the binary number that you want to, the binary stream that you want to just to convert to the, you have the binary number, sorry, that you have to convert to the stochastic representation, which means the binary stream. And then you have a comparator, and then you have some threshold. Then you go up and down, and you have 1 and 0 at the output of this comparator. And from binary to stochastic, what you are doing at the right side is that you have the binary stream, which is the stochastic representation, and you count the number of ones, and then you have the binary number. So for highly non-linear functions that you need, for instance, for convolutional neural networks, like, for instance, tangent, hyperbolic, or maximum function, what you have is that you can implement it, but with the finite state machines. And I'm not going to in details of that, but it's more complex. But you have also circuits that can do highly non-linear functions that is quite important just to apply stochastic computer for a broad range of applications. So if you look to the technology, again, back to the technology, you have invertible logic implemented in CMOS technology by using Boltzmann machines. And these Boltzmann machines are, you have some randomness in these equations that you had with the tangent hyperbolic, and then you are updating according to a matrix which is J, and you have some bias, which is a vector H. So the hardware that is implemented in CMOS is in this first picture, and you have the matrix J and the vector H for a single AND gate. And you can just extend it for different arithmetic operations. And what is quite interesting is that if you look to the figures that you have the Boltzmann machine architecture, you are doing that with stochastic computing. So you are doing multiplication with hands, and we are just applying what we have in stochastic computing. So stochastic computing is a very fundamental type of arithmetic for applying in an efficient way Boltzmann machines to do invertible logic in CMOS technology. So you have several implementation in research works. For instance, you have a 5 Wi-Fi bits multiplier, divider, and factorizer. Because it is invertible, you can do multiplication, and at the same time, you can apply the sum circuit for division or factorization, and it is 13 times. It requires 13 times less area than the corresponding binary for the 65 nanometers CMOS technology. So let's go and see the example for superconducting quantum devices. And once again, in this case, what we have is a diabatic quantum flux parameter logic family. In this case, is a single buffer. So we have some superconducting loops containing two Josephson junctions that are shunted by this inductor, which is the L key. And so with these junctions, you see on the right and left side, you can just store the logic level 1 for the bit and the logic level 0 for the bit. And what is quite interesting is that the characteristics of this type of quantum devices are quite suitable to implement stochastic computing. I'm not going too much in detail, but I would like to say that the main advantage I can summarize by saying this type of technology or device based on this technology, in this type of devices based on this technology, the gates are connected with AC clock signals, which requires a clock phase, which means that it's difficult to avoid read after write hazards if you do binary type of architecture. So if you just think in this type of very deep pipeline processor that you have nowadays, so with this type of logic in each one of the stages of the pipeline, you have inside several stages because of the technology. And with stochastic computing, you don't have this type of traditional architecture, so you can avoid this type of disadvantage of the logic. On the other hand, even with these simple buffers, as I depict in this picture, you have the opportunity of having true random number generator, which is difficult to implement with current CMOS technology. So, and these random number generators, as we have seen, are quite important to do stochastic computing. So I will show you a processor that has been implemented in CMOS technology. So I'm I do not only look to the new emerging technology, but I give you a picture also what is implemented in the more traditional technology. In this case, once again, with 64 nanometers. And what we have is that we have this SNG, and the SNG are stochastic number generator around. Then you have stochastic processing elements. You have a two-dimensional array. You have typically you have 15 by 15 in this Thorne processor, which is a stochastic recognition and mining processor, which means that we use it for recognition and mining and data mining. And what we see is we can have 1 order of magnitude less circuit area and power consumption that if you apply traditional techniques for recognition and data mining. So which means that you have in practice, you can see in practice the importance of this type of new or unconventional arithmetic, and not only on current technology, but you have also, you can foresee the importance of this arithmetic in the emergent technologies. So let's just go to the last type of unconventional arithmetic that I would like to talk with you. Real unconventional arithmetic, which is hyperdimensional computing. And in hyperdimensional computing, or hyperdimensional computing is inspired in brain-like operation. So for that type of computation, you have random high-dimensional vectors. So typically, you have a 10,000 big vector, or this order of magnitude. And this is a real alternative to support vector machine and convolutional neural networks for certain type of classification. So what we use is, on the basis of this type of arithmetic in computing, what you have is that you have associative memories. So you have a pattern hex that is stored using another pattern hex as what we call, you can call the address, but it's not the real address of the memory. And later, you can just retrieve this X by using not only A, but something that is similar to this pattern A that you use to store hex. And like this, you can have a set of vectors in a certain class that can be represented by a vector that is this vector X that is stored in memory. I would like to call your attention that this high number of bits does not at all improve resolution. So it's not possible just to give some meaning of a vector with 10,000 bits, which is a large number of bits. So the main advantage of this type of high random dimensional vectors is that they are tolerant to errors and component failure, because you have many patterns that are equivalent. And if you think, this is also what we have in stochastic computing. And you have highly structured information, like in the brains, that can deal with arbitrariness of the neural code, what we can consider neural code. So the question at this point is that, but which kind of arithmetic do we have behind this hyperdimensional computing? And it's relatively simple, but it's different, quite different from the traditional arithmetic. So you have, for instance, component-wise addition of a set. So you can see that this sum represents a set of individual vectors, because you have to have a vector that represents a class. And so you can use the traditional algebra that we learn and do addition of the vectors just to get the sum. And we can do multiplication. But this multiplication, if you use bipolar representation, as we have to do in stochastic computing, but instead of unipolar, you have bipolar. So with XNOR, you can do multiplication of two vectors. And it's quite important to see that the multiplication maps points. For instance, if you have the vector X and you multiply by another vector M, you map the vector X in a new vector XM in space that is as far from X as the number of ones bit in this other vector M that you use to map. So this means that if m is a random vector, the multiplication just randomizes the vector x. So so we talk about Hamming distance in this type of arithmetic, so hyperdimensional computing arithmetic. So if you see the distance between xm and x is the Hamming distance between so if you multiply xm by x, if you multiply xm by x, you get exactly the xm is m multiplied by x, and then you multiply again by x. And if the multiplication is XNOR, so this means that you get a vector with all ones. So it's like a vector that's multiplied by hem and gets exactly hem. So the distance, the number of ones that you get from this multiplication is exactly the number of ones that you have in the original vector m that you use to map the hex vector. So you have several properties that are important in this type of arithmetic. For instance, multiplication is distributive over addition, and they implement a mapping that preserves distance, which means that if you just multiply by hem, you keep the distance, two vectors, you keep the distance of the original vectors that you have, x and y. So let me just see that this hyperdimensional computing is applied already on nanosystems. So they have been used to do an end-to-end brain-inspired nanosystem using heterogeneous integration of multiple emerging technologies. So in this case, nanotube field effect transistors, and also RRAMs, which are resistive random access memories, to do computation also in memory. And there are 5 grained and dense vertical connections between computations. And this type of integration that performs hyperdimensional computing is performed mainly on memories, but you have some processor elements, and you have to implement them with nanotechnology. So you have also other more conventional or implemented in more conventional technology, hyperdimensional computing processors. So as you can see here, the architecture, so you have an item memory that stores a large collection of random hypervectors that map symbols to items in the inference phase as it was trained in the training phase. Then you have these DPUs, which are processing units that just combine the hypervectors sequence according to the algorithm and just compose the hypervector that represent a class. And then you have the associative memory that stores the trained class hypervectors that deliver the best prediction according to the Hamming distance that you have stored in this associative memory. So I would like to go next to other types that are not related directly with new arithmetics, but so I will go very briefly because I would like to spend more 5 or 10 minutes at the end just giving you some or providing you some experimental results. So Deriah-based computing is another type of non-conventional computing. The arithmetic that I'm going to talk is binary arithmetic, but the substract is completely different. So I just put in this presentation a type of model, the model that we call DNA sticker model. That's what we have is that you have a memory strand, which is a long DNA molecule that is subdivided into non-overlapping segments. And then you have a short sticker, a set of short stickers. So when a sticker is complementary to one of the segments, it represents a bit 1, or the logic value 1. If it is not the case, the segment is not complemented by one of the predefined stickers in the set, so you have the logic level 0. So to have an idea how to implement algorithms in this type of logic, so you have some tubes that you have the strands inside. In this case, you have 2 source tubes, TS1 and TS2, you the power blank strand of n bits in the destination, which means the destination is, you can consider it as a DNA strand with all zeros with no complementary stickers. And then what you do is that you combine both strands in an auxiliary strand, in an auxiliary tube, and then you go bit by bit and apply an operation that we call separate, that goes to the bit high in the strand, and if this bit is 1, it goes to the tube B1, and if it is 0, it goes to the tube B0. And I applied that to tube TA that already had these two strands, TS1 and TS2, and then I just check if B1 is 0, it means that the bit in position 1, in position Y of TS1 and TS2, both are not 1, which means are 0. No. So you are sure that bit 0 is empty, which means that both TS1 and TS2 are 1. So you set the bit on TD by put a sticker on the top of strand, and then you combine again B1 and bit 0 in TA, and you just iterate. And you have several arithmetic units already implemented. For instance, 1-bit full adders, logic operations. Once again, why is it related with unconventional computer arithmetic? Because you have to overcome the negative effects caused by defects and instability of the biochemical reactions and errors in hybridization. So what we do is that we apply redundant residual number systems, and you have works on that from the side of biology and also computer science. So you define a set, you use this type of redundant residual number system representation, and then you can detect errors by applying this unconventional arithmetic, making more reliable the DNA computing, and simplify the DNA encoding scheme. So you apply it in practice unconventional in DNA for DNA computing. So unfortunately, I think I don't have time to go through quantum computing because I would like to cover, and this is not real related with unconventional logic at the moment, but it covers a set of different problems that are related with arithmetic. So I think we should do research on quantum computing, or also on the perspective of unconventional arithmetic. But is a more unexplored topic, so I will just skip this part. You know that a quantum bit is completely different of a bit. So you define an orthogonal basis states, and then you have this 0 and 1, and this kind of superposition. And you have also other properties that are important. So you have some simple single qubit gates. There are two algorithms that are quite important in quantum computing. One of them is quantum Fourier transform. That it's the one that supports what we call the Shor's algorithm, that just break the current crypto systems. So the principle of factoring for the RSA, and discrete logarithm for the ECC, which is the elliptic curve cryptography. So I will skip this part and go immediately directly and try to just to go a little bit faster. So one of the applications that I chose is the lattice-based cryptography. So this is quantum-based resistant. So in lattice-based cryptography, you have a lattice. The lattice is defined by a basis, which is a matrix or a set of vectors. These matrices are defined in different dimensions, units, across the different directions, and you can linearly combine these vectors just to define the lattices. So typically, I have here a representation of a two-dimensional space, but typically we work with 400, 600 dimensional spaces. And what you have is that you define vectors on these lattices. So how do you just briefly and summarizes, make it the concept simple. How do we encrypt a message? So in this case, you define the lattices or the matrix that define the lattices. In this case, in two dimension is this vector h0 and h1, and I define a set of points. And then in this case, I calculate h0 minus h1, which define the point of the lattice that is under the x-axis. And from this point, I will have my message that I want to encrypt. And this message is P. You can consider it as noise. It's a small vector. And then the cryptogram is the vector C. And this is the cryptogram that you are going to communicate or to store. If you see this H0 and H1, we called it a bad lattice because it's far from being orthogonal, these two vectors, H0 and H1. And then to decrypt the message, what you have is that you have another lattice, so you don't know the basis of the lattice that were used for encryption, and you have another lattice that you use for decryption, and these are only owned by the people that is going to decrypt. So you can consider it as in asymmetric public key cryptography, you can consider it as the private key. So the basis of this lattice. And once again, you have in this case the R0 and R1. So this is what we can call a good lattice because the vector is almost orthogonal. And what you have to find is the closest vector to the C point, that is the cryptogram, which is in this case is R0 minus R1, and then you subtract the C from R0 and R1, and this is the message that you decrypt. So I'm not going to usually we use what we call Barber's round of algorithm. You first rounding the components to the integer space because you have it is in a real number space. And then you have to go back again to the canonical basis. And this type of algorithm, what we do is that you use the special case of the closest vector problem. So it is a bounding distance decoding problem. You have it here, the algorithm, but at the end, you have to compute these equations that you have here. And it's interesting because if you look to the right side of the numerator of this expression, you see that you are calculating the remainder of the division of the left part by the denominator 2D. And 2D is the determination of the matrix. So I don't have time to go too much in detail of the algorithm, but we implemented the algorithm in a GPU using residue number system. So I didn't tell anything now. What we did with this quantum resistant type of lattice-based cryptography, but we have applied residue number system to do the Montgomery multiplication with reduction, which is a fundamental operation in the algorithm that I've shown you before. So we implemented in a parallel devices, in this case in a GPU, and using also the multimedia extension for the CPU, in this case an Intel processor, an iSet core. And we do it for dimension spaces which are in n equal to 400, 600, 800, and 1000, which are typical values for this type of lattice-based cryptography. And we have the sequential time in terms of number of clock cycles that is required in the first row of the table. And then we apply RNS decomposition and use the channels just to perform parallel computation either in GPU and on the CPU. So in the brackets, you have the speed up, and you see that in the GPU, we have some speed up when we apply this type of RNS-based decomposition in a Pascal architecture of the NVIDIA GPUs. GPU, so GTX 780, for instance. So we have speedups that between, let's say, 6 and 3.5, which are not really impressive. And the not so good news is that when we increase the size or the dimensions of the lattices, so the speedup decreases, which means that we have a lot of computation that is not performed in conventional arithmetic. And this is done sequentially, so we cannot take advantage of the parallelism that is provided by the residue number systems. And at the end, at the last and the bottom line of the table, you have exactly the extension of the algorithm with residue number systems for the Montgomery multiplication with reduction, with 4 cores, but now using AVX2, so 412 bits, which represents, considering 32 bits, it means that we are implementing in parallel 16 32 bits. And we can expect at the maximum 16 as the speed up, and we have 11.2 up, down to 8.2 when we have 1,000. So the conclusion is mine. I give you, because this is the experimental results, is one of the research, that we have done 2 or 3 years ago. So you have real numbers, in this case for traditional technology. But since we are able to exploit parallelism, we can apply it also for emerging technology. The other one is convolutional neural networks, in this case, YOLO version 2, that we have all these convolution and also pooling and fully connected layers that you have in CNNs. So if you go to this 2D convolutional operation, is quite straightforward to apply residue number systems. So in this case, it's not our group that did it, but do fully parallelization in FPGA using residue number systems and go a step forward. So you have on the left side, you have the traditional architecture. On the right side, you see that we are exploiting parallelism because you are splitting these tree of additions and multiplications at the bottom, and then additions in the different channels of the residue number system. And it means that we can exploit once again and do in parallel. Either we have technology or in new technologies or on the current technology by exploiting the hardware that you have. So we go a little bit further and do 2 different levels of the composition of residue number systems, which means that we decompose a large model into even smaller modeling. And we can even take advantage of the fact that in the 2 layers you can have the same model. So I'm not going to explain the arithmetic too much in detail, but looking to the architecture, what you have is that you have the first binary to residue converters, and the 3 channels that you have, one of them requires 3 bits, and then the other 2 4 bits, which is not adequate for the hardware that you have to fit exactly the size. So what we do is that we decompose again and make residue. Once again, in this case, binary is not binary because it's are already residues, but we decompose again in another level of residues. And all the inputs of these lookup tables, you have 3 bits. So it's quite homogeneous. So we have applied it. We call it nest residue number systems to real convolutional neural networks with several layers and with different characteristics. So you can see in this table. So then we have the slides and can go more in details. We got what we call the mean average prediction. So around 70% is well classified. You implemented it in FPGA, so with the resources that you know for typical FPGA, so with LUTs and lookup tables, and also with DSPs, so with 9-bit fixed precision, which means 3 bits, with a dynamic range of 30 bits, So we achieve around 4 frames per second at 3.5 watts. So the conclusion is that if you do it not in an FPGA, but on a GPU, you can get much higher speed. So you can compute 21 frames per second, while in the FPGA, you only compute around 4 frames per second, but the power consumption is completely different. So if you look to the efficiency in terms of frames per second per watt, is 1/3 when you compare the GPU with the FPGA. So I think I'm exhausting the 1 hour, so let me just give you briefly the conclusion. So we can say that a conventional data representation and arithmetic, I hope to have to convince you that are fundamental for computing with emergent technologies. So I gave you examples, but at only a very small subset of examples. But let me just go back again a bit and say that, for instance, for residual number systems, we use redundant residual number systems for DNA computing. We use stochastic computing for adiabatic quantum flux parameter logic. We used HDC, hyperdimensional computing, for nanotube field effect transistor and resistive RAM together in a heterogeneous system. So I would say, and I would like to point out that this is exactly what I'm trying to write, and the message that I would like to give you today by the very end of this presentation, and I will pass also in the survey that I'm preparing. And I think it's quite important for people that are investigating this topic, is that for investigating unconventional arithmetic, we must consider all the dimensions of the systems. Otherwise, we are doing what I can call it more academic research. And it's important to include not only computer arithmetic theory, and in this survey I will put a lot of this theory, but in this presentation I just skip all the theory. But also we have to do it in parallel with the technology advance and look to the demands of the emergent applications. So thank you very much for your attention. I can just answer some questions and answers if you have it now.
Dr. Sosa, thank you very much for the presentation. We do have a few questions, and if anybody has any questions they'd like to ask, if they could just put them in the Q&A area. Let me give you the first question that we have here. This one person has asked, who has done or implemented the end-to-end brain-inspired HDC nanosystem?
I can put I don't have it in just by heart, but I can send to you. You can drop me an email and I will send to you. But I think it's from Intel, IBM, and also university, I think Princeton. But I have to make sure and give you. And is a joint project, and they have implemented it. So, but I'm not completely sure. But there is for sure some implementation. So I can send you if you drop me an email.
Great. The next person asks, in some number representations, overflow, sum, or product may exceed the number of bits used in implementation of the hardware. Is overflow easy to detect by hardware in such number representations?
So this is exactly one of the problems that we have, and I told it when I presented this type of unconventional number systems. In some of the representation is not easy. For instance, in residual number systems, it's hard to detect overflow. You have algorithms, and you have some hardware implementations of these algorithms for particular moduli sets. Typically, the three moduli set, the traditional three moduli set, which is well known, and I'm not going in details, but you have work for that. But you don't have any general method or algorithm that you can apply for all the moduli sets. So what we do in this case is that we are not sure. Either you are conservative and you define a range that is larger enough to accommodate all the computations that you have to do, or you use some kind of redundant residual number systems, which means that you have an illegitimate range that you just keep for the case that you have overflow in the legitimate range. But you pay for it because you have to make the algorithm a bit more complex, and you have to implement it in hardware. So the answer is, in this type of unconventional number systems, at least for part of them, is more difficult. More difficult just to detect overflow. For instance, if you are doing it in stochastic computing and you have an unlimited number of bits in your bit stream, you really don't have your problems because you are representing numbers between -1 and 1 or 0 and 1, but you have the range. What you are talking is about accuracy. But in this case, you trade dynamic range by accuracy. So because if your bit stream is not long enough, so you are doing approximate computing, and you can have large errors. So we have to be careful. So this type of conventional arithmetic is not as much research as the binary systems. So that's why I said we have to continue and keep going on this research. But for sure, in the future, we will find more efficient methods for this kind of limitations.
Thank you. The next question is, which number system would you recommend to perform module and prime arithmetics?
I would say residual number systems. What we have in model, forget the fact that you are reducing by a prime. But if you are reducing by a number, which can be a prime or a coprime number, and a coprime means that you are relating with other operations that you are doing, what we have is that mainly what you are doing is multiplication with reduction. And it just point out you to the Montgomery algorithm. So the Montgomery algorithm, what we do is that we apply it in binary systems, and we map this reduction that can be, and in your case, in your example, is a prime number. You map it in a domain that you do it in binary systems, in a binary system. So what we do is residual number system is that we don't do it in binary systems. We do it with a moduli set that is defined by a residual number system. And there is a lot of work on that. So I can tell you that one of the pioneers was Jean-Claude Boisjard in a university in France, so Paris Marie Curie. I did also a lot of work on that. What we have to do is to define two moduli sets, because you are not able to do all the Montgomery reduction algorithm with a simple moduli set. So you define two moduli sets, and then you have to map from one to the other just to apply the Montgomery algorithm. But it's relatively efficient, is what I have used in this example that I presented you with results in a GPU. And you can apply it not only for parallelizing, but also for, in a certain way, for simplifying your reduction when you are doing multiplication with reduction.
Very good, thank you.
Let me just say that. Sorry, Kerry. Let me just say that we are applying at this moment also stochastic computing for cryptography, and in this case, not for modular type of computation that you apply in cryptography, as the case that you referred before. That is a typical application of model with prime numbers, but is more for homomorphic computing. Because in homomorphic computing, you have to decompose your processing in some kind of binary gates. So if you have your stream of bits, so you can apply stream computing. So we have a very nice, a very interesting recent paper from last year, that we show that with stochastic computing you can apply homomorphic encryption, which is a type of encryption that you can process directly in the encrypted domain, and you can do it, for instance, you can do it with stochastic computing. For instance, if you talk of servers and this type of remotely processing, that you have cloud computing and you don't need to decompress or just resend to the one that have the private key just to decrypt the message. So go ahead, Kerry. Sorry.
That's okay. Thank you very much for that answer. The next question is, did you program your FPGA designs using HDL, Verilog VHDL, or higher level means of design entry like HLS or OpenCL?
Okay. So this work that I presented, which is nested residue number systems, has not been done in my group. So is a paper from, you can go there, so I have some collaboration with them. So it's a paper from ISCA conference, I think almost for sure is 2018, in a special session that I organized in residue number systems. I'm not sure, I think they program in Verilog, but I'm not sure. We have to go and check in the paper. So if you ask in my group, what we have been done is more and more to use HLS, because we want to just evaluate what is the impact of this type of unconventional systems in new emergent technology by simulating, or in traditional architecture, in traditional technologies but using current architecture. So in both cases, we would like to know exactly what is the improvement by using this type of unconventional arithmetic. So we move more and more to high-level synthesis, but we have to be careful, because when you describe the arithmetic, you have to put in line in your description the arithmetic units that you have. And this is quite fair, because when you use HLS with traditional binary systems, so the design automation tools for sure do the best for achieving the best units and arithmetic units that you can have for binary systems in this particular technology. So when you do is that you patch these unconventional arithmetic units that you optimize for the technology that you are talking about, and you use it in HLS descriptions. Because to do everything in Verilog or VHDL, it's quite time consuming. But you have to be careful. And the comparison is fair, because you don't have yet optimized tools just to synthesize your unconventional arithmetic unit. So the answer is we use both. So mainly we try to use HLS, but we have to go deep into the RTL description when we are talking about the unconventional arithmetic units that I described in this, and I described in this talk or in this presentation.
Very good. The next question is simply, where will your survey article appear and when?
Yeah. So I hope it is accepted, because it's some kind of already. So in these journals of IEEE, we first apply with the first proposal that you have 4 pages or something. It's not a white paper, but it's the proposal. and then you get invited to write the paper. So I just passed this first phase, and if it is accepted, so I'm finishing it. It was supposed that I finished it 1 month ago, but I'm teaching online, so very busy this semester. So I will hope to finish it before the end or by the end of July. And if it is accepted, it should be published somewhere in the last quarter of the year, and it will be published in IEEE Circuits and Systems magazine.
Okay, very good. I think maybe we'll take a couple of more questions. We're a bit past our time.
Sorry for advertising, not the Computer Society, but in this case it's the Circuits and Systems Society, because it's a work that just combines the arithmetic, which is the computer science part, with the technology, which is the circuits and systems part.
That's perfectly fine. So this next question is, the person is working on stochastic computing, including image processing and neural network case studies from more software modeling and testing perspective. The question is, what is the most suitable number, unconventional number representation for neuromorphic computing? Can we say that SC can work well as a noise-robust alternative? And is it possible to get your valuable slides? Well, the slides we will send to everybody, so as a PDF. But the other questions, perhaps.
Yeah, so thank you very much for the question. I think it's a very interesting question. Unfortunately, I don't have an exact answer. But either you use SC or HDC. So if you, let me just say, why SC is interesting for neural networks since the beginning? Because this is the type of application that you apply intrinsically approximate computing. So you don't have to have the exact result. You have to, at the end, choose the right class if you are classifying, or the right identification. So you don't have to have an accuracy, defined accuracy quite perfect. You can do approximate computing, and you just work with that by enlarging or shrinking your stream of bits. You cannot do it in HDC. So I would say that if it is in general for neural networks, so stream computing, maybe it's the better solution. And you can adjust the example. I didn't give an example with stochastic computing, but there is a lot of examples with stochastic computing for neural networks. But if you are doing classification in a very noisy environment or technology, for sure, hyperdimensional computing is the solution. And if you are doing classification, why? Because you can see if you just pick up a binomial distribution and get the numbers, is quite interesting, because you have an n-dimensional space. I don't know if you realize, but 10,000 bits, which means that you have 10,000 dimensions of your space. You can imagine a hypercube with this number of vertices. And if you look from a point that you have a vector, so you have a large number of vectors that just change the combination, but there are around in a vector space that is close to this one. And you can make several mistakes, and you are in this narrow band, which means that you have a class of vectors in this large space that can be considered almost the same. And that's why I said you have a pattern A, but you can just retrieve the information or get the information with a pattern A, something that is near A, because you have, with this type of distribution, you have randomness that allow you to have a large set of vectors that are close to this one, and then you have small numbers that are large to that class of vectors. So I would say that the answer for your question will be, so for general neural networks and if you can have some control on the accuracy, I would say stream computing, but look to hyperdimensional computing, because you have a lot of, so not only works, you have a work from, I think, 2009, that is a seminal papers in hyperdimensional computing, that you can go there and have the basics of arithmetic. But you have also very recent papers, for instance, in the IEEE computing, in IEEE proceedings, and also in other journals. For instance, Luca Benini in ATHD are also doing work. So people also in Berkeley are doing very quite interesting work for IoT and cyber-physical systems. So you have a not only theoretical solid background, but you start having very interesting practical application of HDC, which means hyperdimensional computing. But the arithmetic is quite different. So you have to be used to go a bit to the distribution and see how do they work in the hyperdimensional space. Think a bit about arithmetic as Hamming distance, and the arithmetic as mapping vectors in this hyperdimensional space. And the properties are quite interesting when you do that. So multiplication becomes mapping vectors. And if you do the mapping of two vectors, as I said in the presentation, so the distance of to these mapped vectors are exactly the same as the original vectors. So you can play around with arithmetic, which is not quite complex, but with a large number of bits. So hyperdimensional computing is also interesting for processing in memory, because you do most of the processing that are not complex close to the memory, and you have also associative memories that is a kind of special memories that can be performed better if you do the processing near or inside your memories.
This last question may be better through email, but just if you know off the top of your head, are there any books that you can recommend on residual number systems?
Okay, I cannot advertise my books. Maybe maybe it's not proper to do that. I think if you have a book from Mohan, which is M-O-H-A-N, so he's an Indian colleague. And the book is from 2019, it's from Springer. I think is the best you can have in residual number system. So you have everything there. Mohan is one of the pioneers working on residual number systems, and just provide a very, very interesting book. I can not give exactly the title, but is from Springer, is from 2019, I think. Is Mohan, I think is M-O-H-A-N. And go there, and if you can buy the book, is the best that you can get. We have a book, so myself with Shipong Shang from NTU in Singapore, and also Amir, that is now a postdoc in Belfast, that is called Unconventional Number Systems for Embedded Systems. And you have 2 or 3 chapters. It's a book also from Springer, I guess from 2017. And if you go there, I think you have a couple of good chapters about residual number systems. But you have also logarithm number systems. So you have other types of unconventional number systems. And it's more related with embedded systems that you take in consideration. So the energy consumption that I didn't have time just to talk today about, also these acts of the systems when you design with unconventional number systems. So I would say that this book from Mohan from me is the best one in residual number system, and it's very. So it's very actual. So you have everything, and you have all the reference in the last 21 that the research that has been done in this type of unconventional arithmetic.
Dr. Sosa, thank you very much for giving us your time today and giving this presentation. You've given us a lot of different unconventional number systems to think about. I also want to thank everybody else for attending. Our next webinar in the Distinguished Lecturer webinar series is going to be on the 16th of July at 6 a.m. U.S. Eastern Time. Dimitrios Serpanos, Professor of Electrical and Computer Engineering at the University of Patras, will cover smart and circular cities, status, trends, and opportunities. This webinar will be co-sponsored by the STC on smart and circular cities. In addition to the Distinguished Lecturer webinar series, we also offer a Build Your Career webinar series that focuses on business soft skills such as communication, presentation skills, career transition, interviewing tips, among others. Our next Build Your Career webinar will be on the 22nd of July at 11 a.m. Eastern Time on Lead Yourself First by Adam Schmidt, CEO and Principal Coach at Smart Summit Coaching, LLC. Registration is now open, and we will be sending you links to these future events along with the slides and the recording of this webinar. Again, Dr. Sosa, thank you very much for today. It was a wonderful presentation.
Thank you very much. Bye-bye.